Okay. All right, so we're going to go through a little bit on states of matter and leading into the discussion on vapor pressure. Okay, so here's our states of matter, and as we have talked about previously, the places that we care about intermolecular forces are primarily when we're talking about solids and liquids. All right, so here we have this, and this is showing our phase transition. There it goes, moving. Okay, and so we are cooling this down. So you can see the little thermometer moving down, and as it cools down, we get a slowing of the molecules, right? Because temperature is a reflection of average kinetic energy. And then also you can see as it slows down, I don't know if you can see like right in here, these guys, the intermolecular forces start to take a play. And so now we are going from a gas to a liquid. So we are condensing at this point. They're starting at the slower they go, the more heat that's removed, then they start to interact with each other. And then as it gets even cooler, we start to get some order to it, and they start to get more locked into place, a little less flowing past each other. And as a solid, then we just get the vibrational motion. Strong intermolecular forces and with only vibrational motion. Okay, so vaporization, we're going from a liquid to a gas. And so the enthalpy of vaporization is how much heat that it has to absorb to convert a specific amount of a liquid to a gas at a constant temperature. Okay, so if we had, in other words, if we had if we wrote, in this case, we're going from, say, H2O liquid to H2O. So if I wrote this equation here, then the delta H that I would write to go with that would be this delta H of vaporization. Okay? All right, and so in your book there are tables. These are tabulated values. These are at a standard temperature of 298 Kelvin. Okay, so first thing to notice is that when we're talking about enthalpy, if you remember, standard temperature is not the same as it is if we're talking about ideal gas laws, that kind of thing. So standard temperature, if we're talking about enthalpies, is 298 Kelvin, or 25 degrees Celsius. Oh, okay. All right. So vapor pressure of liquid is partial pressure, meaning the pressure due just to that liquid when it is in equilibrium with the liquid phase. All right. So we're going to look and see what that means. I have like a little animation here that's going to show that. All right. So here, let me get rid of my arrow back so I can click on this. All right, so here I have a liquid. We've capped it. All right, this is a little manometer, right, attached to the vapor space so we can see the change in pressure. And this is plotting. This is how fast are gas molecules leaving the surface and becoming, or how fast are liquid molecules leaving the surface and becoming a gas. And then this bottom line here is going to show how fast are the gas molecules hitting the surface of the water and getting basically captured. The intermolecular forces lock in, and the molecule does not have enough energy to re-escape. All right, so we have, anytime we have evaporation going on, we also have concurrently condensation going on as well, especially if we're talking about a closed container like this one is. All right, so here, and remember, we're not changing the temperature. Vapor pressure is temperature dependent, so we're going to hold the temperature constant. So initially, when we first cap the container, we start to see some evaporation occurring. Okay, and primarily that's what's going on. But then at some point, we get enough gas molecules in this vapor space that they do start to come back and collide with the surface of the liquid and recondense. Okay, and so the vapor pressure is the pressure, because eventually you're going to get to the point where the rate the number of molecules per second that are condensing is equal to the number of molecules per second that are vaporizing. And once that happens, that's the point at which we measure vapor pressure. Okay? Oops, sorry. I mean to start that again. Okay, so the intermolecular forces are basically the thing that determines what our vapor pressure is. Because the weaker the intermolecular forces, then the more molecules that will go up into that vapor space, that will be in the vapor space at any given time once the equilibrium is established. Because remember, the thing that's going to make it vaporize is, remember, temperature is an average kinetic energy. And so you're looking to see when, by random motion, the ones that are in the liquid, when they hit the surface of the water, do they have enough energy to break free? The weaker the intermolecular forces, the more likely it is that it's going to have enough energy to escape the surface and become a gas molecule. Okay? It's going to increase, vapor pressure increases with temperature, which kind of makes sense. The higher the temperature, then the greater the number of molecules that are going to have enough energy to escape the surface of the water. And so vapor pressure, which we saw when we did gases and did Dalton's law, where if you were collecting a gas over water, and so you had to look up the vapor pressure of water at a given temperature. Okay, that's what this is. So there are tabulated values for common substances, and here's one for water, which is one you should be familiar with. Okay. All right. Volatile liquids. Okay, the term volatile easily evaporates, so they have very high vapor pressures, which means very weak intermolecular forces. Okay, and so here's some example vapor pressure curves here. We can look at these substances and kind of see. So here we have, let's see, CS2, that's going to be a nonpolar substance, so it's got our lowest. Then we get methanol as the next one, and has kind of a, wait, which way are we going here on this? Vapor pressure at atmospheric. Oh, I'm reading it backwards. I'm sorry. Temperature. Let's try that again. I'm looking at the thing backwards. Okay. All right. So here we've got a comparison. Here's some hydrogen bonding here, and actually a larger molecule, C6H5. So it's going to have stronger forces, and then water be a little bit weaker. And then we've got some hydrogen bonding in both of these alcohols, but a little, like maybe a little bit of London dispersion from the extra piece of the carbon chain here for the ethanol that's in there. So, and again, the higher the stronger the force, the lower the vapor pressure. Okay, and here's definition: normal boiling point or normal melting point. That is the boiling point at 1 atmosphere of pressure. Okay, so anytime when you're looking up a boiling point, it's the ones that are reported in the tables are the normal boiling points. That's at 1 atmosphere of pressure by definition. And so again, that's what this line up here is representing. Let's go to that line. This line right here, 760 torr, so that's 1 atmosphere of pressure. And so it's showing our boiling points, all right along here. And so boiling points, which we don't have one there for the last compound, but our boiling points are a function of the strength of stronger forces, higher boiling point. So here we have water at 100, okay, which we're familiar with, and then you can see as the forces get weaker, our boiling points go down. All right, but then looking on the side here, forces get weaker, vapor pressure increases.